Hi guys, alright, so we are back. This is 3.2 on your earth structures, mainly on the dams and embankments, right? So let's roll. Okay, these are examples of embankments. Essentially, embankments simply means a structure, an earth structure that is long. Alright, as you can see here, you compact the earth to form a higher level, and they are essentially long. Why? They are usually for roads or rail tracks or runways, anything that is long. Okay, so the first type of embankment that you see here is actually a homogeneous one, where the whole embankment is from one type of soil. Right, and typically you have a paved road or rail track on top of it, and on the left and right side of it, on the slope side, you have vegetation to prevent erosion. Okay, and the second type is the type is a layered type. As you can see, the one that is the yellow strips that I put in there for you are actually the fine grained stuff that you can find in adjacent land, meaning that on site you could find these, whereas the other layers, coarse material, they are imported. Now, generally, we would want the embankment to be built of coarse-grained materials. Why? Number one, they are stronger because they interlock among themselves, like gravels and sand. Number two, they are free draining, so we would not have problem of a groundwater table that is high accumulated in there and affecting our effective stresses and the strength. Alright, and the third type, as you can see down here, are actually those that we usually find along canals or rivers, where on one side they are actually facing the water. And in this case, a canal in BM, easier said, is like parade. Okay, and to protect the embankment from erosion, usually there's a concrete lining here. Okay, and on the upstream side, that is on the side that is facing the land or the land, we have usually a toe drain at the end. We will see more in detail about this later on, don't worry about that. So this is for embankment. And what about earth dams? Earth dams, as the name tells, it is made of earth, obviously, and this is definitely, as is a dam, is surely certainly impounding water, meaning that it's containing water on one side. So the side that's facing the water, we usually call them the downstream, alright? And the one that's facing outside or the land is called the upstream. So the first type again is like just like the embankment, they're homogeneous of one soil. And the second type, it has a thin core in the middle that's impervious. Remember, when it's made of earth, then water will tend to want to flow through it, right, onto the other side, and that's what we don't want to happen. But bear in mind too that that is unavoidable. Some water somehow will be able to come through, but as long as the seepage velocity, alright, the velocity of the water flowing through the soil is not too fast, then it's alright. And number two, more importantly, it is not carrying materials with it. It's not carrying soil with it and leaving a void in the embankment or the dams, then it's alright. Hence, we have this core in the middle so that the water can be intercepted, any flow coming through from the downstream. The third type is a zone dam. As you can see here, we have in the middle, you have an impervious core, whereas on the sides, you have semi-impervious cores, semi-impervious soils. Now, this situation will happen when we have, we do not quite have enough good soils to form the impervious core in the middle. So we probably have to compromise by having a second type of soil that's imported from a nearby site. Instead of having to import the whole lot of soil, that is a pervious shell that you have probably plentiful around the area, then we might as well make use of what we have. Okay, so now we go into details of how an earth dam will look like from inside till from inside out, right? Picture wise, you can see this is how they look like. This is where the water is being contained, and this is your earth dam. This is the downstream, this is the upstream side facing the outside, and usually there is an inspection road over it, alright, for the inspection and monitoring works and maintenance works to take place. Okay, so a cross section of it. We start by looking at the core. Okay, now for the core, as you can see, we can have a vertical thin core in the middle, or we can have a thick core. Alright, or it could be an inclined core. The long and short of it is that you should have a core in the middle, and which is made out of impervious soil, which is clay, so that water cannot intercept the earth dam and come through the upstream easily. Alright. And the second part that we would like to look at is the cutoff trench. Note that while the water is being impounded from this layer, from the foundation, top of the foundation to the surface, water can also flow down through this area and up to the upstream area. So that is something we don't want to happen as well, and especially if your earth dam is sitting on the foundation that is fractured rock. So let's look at some of the details. Okay, see, Usually, we will lay a layer of coarse material for the earth dam to sit on, so it's a strong layer. However, we cannot always be certain that underlying it is not the fractured rock. So we want the dam to be sitting on a hard layer, so it should be rock, right? But not all rocks are perfect, and most of the time they are fractured, and when they are fractured, water will tend to be able to flow through it. So a way to get around this problem is that we have a grout curtain. Now, this is cross-section of things. So looking from the front, right, from front elevation, this is what we see. The water, you have your coarse material, and this is a fractured material, and the bottommost layer is the grout curtain. So as you know, grout is actually, if you like, a thick layer, a high viscosity clay, alright, high viscosity clay that will actually expand when they hit water, and hence it will fill up the voids that is in the fractured rock and stop any seepage that may happen. Okay. Next, let's look at the internal drains. So we did say that somehow some water will flow through the earth dam itself. Alright, in such a situation, you do not want the water to simply just flow out, and as it goes, it will actually go, because of gravity, it will go downwards. Okay, and we can intercept that flow by using, number one, a horizontal blanket drain that is horizontally laid, or it could be a vertical one, and we call it a chimney drain. So all you can see now is that in this case, the water flow is being intercepted by the chimney drain and being drained off through the toe away. And similarly, for a horizontal blanket drain, it will be drawn down and taken out. Okay. If water is being accumulated in the dam, you can imagine what's going to happen. Water pressure will build up around the toe area and push this sloping part off the main body of the earth dam, and that can cause, if you like, a slope failure. Alright. Next, we'll be looking at the surface of your upstream and also the downstream. So here we go. For the downstream, we usually can have two types of protection. One is the vegetation. Two, we could have berms coming in. Berms means cuts like steps. So when you have steps like this, as you usually see along the highways on these cut slopes, what we can do is that the berms will slow down the flow of water coming down. If you have rainwater coming down, it will slow it down. So when we slow down the water coming down, we slow down the damage, the erosion forces. Okay, and take note that when we plant any vegetation along the slope, we do have a transition filter in there. We'll talk more about it after this. And on the upstream side, you can see that the one facing the water, because of waves, because of the water dynamics, they usually have ripraps. They are simply rocks or cobbles being arranged nicely and being mortared together. Mortar means cemented together. You can see these very nice pattern rocks, and you have these mortar cementing it. And again, they have transition filters at the bottom. And note that they go from coarse to fine, right? The boulders, the riprap, then the coarse material, then the fine materials before you reach the dam. Okay? Last but not least, let's look at the rock toe bit, which the focus is actually on the toe drain. We did say that if water has been collected down there, what do we do with it? It has to be discharged off. So there are two situations or two solutions to this. One is that there's a rock toe. It's almost like a wedge that you put at the base of your earth dam, so that it wouldn't, the soil mass wouldn't be pushed out. Okay, and there are these transition filters. The ones that are inside is to make sure that seepage coming through can be drained out. The one that's outside is to collect any runoff and also the water that's being discharged from the inside. Okay, if you don't like one that's put outside, a drain outside, open toe drain, you can have one that's embedded. It's a perforated pipe, meaning that a pipe that has holes all over it, so water coming through here can be taken in through the holes into the drain pipe and be taken out. Okay, and for designing an earth dam, there are certain criteria. But before we move on to that, let me take you to some of these criteria that we refer to for the transition filters that we talked about previously. Just hang on a minute. Here we go. So remember, this is a riprap that's on the downstream part facing the water. So these are the rocks that we're talking about. A coarser material, the filter, followed by the finer material. And normally we have a geotextile, some kind of separator coming in to separate the finer transition filter material from the earthen material. So this is a picture showing the construction of it. These transition filters have got mainly two functions. One is to make sure that water coming in can be filtered out. Number two, when the water is filtering through the material, the filter material, it does not take away the soil with it. So not too coarse, not too fine. That's the criteria that we want. And to make sure that that criteria is being met, the certain parameters being used is being, if you are going to take care of the permeability of it, you look at the D15 of the filter material divided by the D15 of your protected soil, and it must be greater or equal to 5. To ensure that the fine particles are not being taken out or do not migrate because of water pressure coming in, then your D15 of the filter over the D85 of your protected soil must be no more than 5. And there's a third criteria, and that is both the gradation curves for your filter and the protected soil should be similar. Don't worry too much about this. We'll look at an example after this. Alright? Okay. So with that, let's look at the design criteria. These design criteria we're talking about here, there are several here when you want to have an earth dam that is safe. Number one, obviously, the water should not flow over the cracks. There should be no overtopping. It should be designed in such a way that the water level will never go over the top of your earth dam. Number two, both the slopes of your upstream and downstream must be stable, and they shouldn't suffer slope failure like sliding. Okay. Number three, seepage must be within acceptable limit. It doesn't say here that there must be no seepage. It says here that the seepage is acceptable. Okay. Number four, the flow along your fitting line, that's the top of your groundwater table, must be intercepted. That we take care of using what? You're right. That's the internal drain that we talk about, the horizontal blanket type and also the vertical, the chimney type. Number five, there should be no migration of fine particles. Alright, while you allow water to flow slightly through the earth dam, there must be no piping or no migration of small particles coming out, leaving voids in the dam. And number six, the upstream face of your dam must not erode or from wave action, meaning that the water that you are impounding will not cause any erosion. Similarly, on the land-facing side, water coming, the runoff coming from the rain shouldn't be eroding the slope. And finally, your foundation must be sound. It shouldn't fail by bearing, it shouldn't fail by sliding, it shouldn't fail by excessive seepage. So with that, we move on to some examples after this.